All right, we're live over here. So this is kind of a new thing. I wanted to start doing my teaching videos live to get, I don't know, I think it's more convenient for me because then it'll automatically be uploaded and I don't have to go through the editing process. And also, you guys can ask questions and I can answer them live because I'll be right here. So I think this is just more convenient overall. I'm gonna try to get the comment section up over here on my laptop. And today we're gonna be doing a calculus video. We're gonna be visualizing the power rule. And all right, what's up? We got one person in the comments. What's going on, Forrest? All right, so today we are going to be visualizing the power rule. So the power rule, I think it's something that we all know. It's a way of finding the derivative. And I thought it'd be nice to take a more geometric approach, a more visual approach to why the power rule works, how we come about it, and why it makes sense. I feel like nowadays, like when we learn something, we kind of just learn how to do it, and it's definitely nice to think about why something works and why it makes sense. I think learning something and not knowing why it makes sense, or like, for example, if you learn something, and this is a weird way that I think about it. If you learn something and if you go back in time and you can't be the one who invents it, then what's the point of learning it? You know, like, it's nice to learn something in a way that you feel like you can be the one who invented it. So the power rule is basically, I think you guys know, it's just y is equal to x squared. So this is just a function. For example, it's multiplying by the coefficient and subtracting, multiplying the coefficient by the exponent and subtracting 1 to the exponent. So y is equal to 2x. Okay, and then another example would be y is equal to x cubed. So you multiply the 3 to the front and you subtract 3 by 1. All right, so this is just something people mindlessly, they just keep on doing the power rule, but it's nice to see how it works. So we're going to be using the function and showing it as area, and when we visualize it as area, we can really see what the derivative of that function means, and we can kind of come up with why the power rule works. So let's get started with the first example. All right, it's better now. Sorry about the lag. All right, let's get into the first example. So we're gonna start with x squared. I think that's a nice function to start off with. So we got y is equal to x squared. So let's imagine x squared as the area of a square. I think that makes sense. We got this square right here, and the area is x squared. So this function is a function of area. So the length would be x, and this length would be x. All right, so the input in this function is length. Okay, that's the x value, and the output would be area. The input is length, the output is area. That's something that helps to understand. And we want to see what the derivative is, a tiny change in the input, a tiny change in the x value, and what's the resulting, and we're trying to find out what the resulting change in the area would be. So what would happen to this square if we did a tiny change to the x value, the input? We'd increase this length by a little bit, this x value by a little bit, and then we'd increase this x value by a little bit. So let's do that. Let's increase this x by a little bit. What do we get? A little increase in area this way by increasing this x. And then let's increase this x this x value by a little bit, which would result in this. And then we have this over here, this square. So we changed this x value by dx. That's the very small amount that we changed the x value by. We changed this x value by dx, and we changed this x value by dx. So the new length is x plus dx, x plus dx, and yeah, that's a new length. All right. Is lagging? Or is it okay? Sorry about the lag, guys. Hopefully it's better once I post it. But I'm gonna keep on going. I don't know what I can do about it. All right. So this is the new area that we get. This is the new area that we get from this resulting change in x. And this would be dy. All of this shaded area that I just did, that's dy. The resulting change in the output, which is area, from the very small change in the input. So dy would be equal to this rectangle plus this rectangle, right, this one, and then this tiny square. And they're all shaded. Okay. So dy is equal to the area of this one, which would be this rectangle. The length is x. The width is dx right here. So it's x times dx plus this one is the same thing. It's x is the length, dx is the width. So x times dx plus this very, very small cube right here, which is dx times dx. And we can simplify this by doing 2x dx. I just brought these two terms together and turned this into dx squared. And one thing we can do is that we're trying to find a very, very small change in x. So our goal is to find instantaneous change, the instantaneous rate of change. So this x value, our goal is to make it approach 0. So we can cancel this out. Dx is basically so small that it is 0. We can get rid of that. And we're trying to find dy over dx, the very, very small change in y divided by the very, very small change in x, which would be the instantaneous rate of change. So if we divide both sides by dx and divide this by dx, we get dy over dx. These dx's cancel out, and we get 2x. dy over dx is the derivative, and the derivative is equal to 2x. And we can check this by doing the power rule that we know. This is our original function. Y is equal to multiply the coefficient of 1 times the exponent of 2, and then keep the x, and you subtract the exponent by 1, which would equal 1, so we don't have to put that. And so yeah, this is a nice way to see for x squared how the power rule works, and it's pretty satisfying actually to come about the power rule this way. All right. Just checking up on the chat there. Let's try one more function. I want to show you guys how it works for x cubed. That one's also pretty interesting. And we'll obviously see that the derivative of x cubed will be 3x squared, because just using the power rule, but we're going to be finding it in a pretty interesting way. So obviously this isn't like something very useful because you know the power rule, you don't have to do any of this, but it's really just nice to see and nice to think about. So let's do another function, y is equal to x cubed. So x cubed, let's think of this as the area of a cube. All right, let's see if my cube drawing skills are on point. All right, whatever. I think that's fine. So the volume of this cube is x cubed. Okay, that's the volume. And I actually want to erase that because it's gonna get messy. But this time we're working as the input is still length, since the length, the width, the height, it's all equal because we're working with a cube, and the input will be length. So this will be x, this is x, right? And then this is x, and then this is x cubed. And I'm just gonna erase all that. I just wanted to do that to show you guys what we're working with here. The input is length, the output is volume, x cubed. So let's get the derivative for this. The reason I'm erasing this is it's gonna get really messy. I'm gonna show you guys what's gonna be happening. Thank you. Yeah, I think it was a pretty solid cube. All right. So we want to see a very small change in this x value, which is the length, what that does to its resulting volume. So let's change this x value by a very small bit. So what happens if we change this x value by a little bit? So let's increase it by a little bit, raise it up. What do we get? We get a plane raised over here. So a kind of increase, a sliver increase in volume this way. Okay, that's this x value increasing. And now let's increase this x value, this length. This would be the width. And then this would result in a cube, not a cube, a plane this way. A little increase in the area this way. And then let's increase this last x value. Increasing this x value would make the object grow towards us. You have to visualize this three-dimensionally. It'll grow towards us. So we get another plane coming out towards us. And then we get a very small cube over here. All right, so now we're trying to find the dy, right? The very small change in volume that is resulting from the very small change in the lengths. So what is the new volume that we've gotten? It's these three new planes that we put and this very small cube. So the first plane, plus the second plane, plus the third plane, plus the very small cube. All right. So we want to see dy is equal to the volume of this cube. The volume of this cube would be, it has a height of x. We can look at any of them. It's going to be the same for each of them. So let's focus on one. Which one did I draw the best? Let me see. I think the top one would make the most sense. So, yeah, let's go with the top one. Okay, so it has a length of x, a width going that way of x as well. So it's x, x, right? And then it was raised by a very small dx. So this would be dx, this sliver, its thickness, dx. So we can put that as the height. So it's length times width times height for the volume of this plane. So it's x squared dx. So it's x times dx. Plus, same thing for this one, x squared dx plus x squared dx plus, this would be dx cubed, because it's a very small cube that is, its length is dx, its height is dx, its width is dx. So dx cubed. All right. We can simplify this. We get dy is equal to 3x squared, because we have 3 of these terms. We can put 3x squared dx plus dx cubed. And again, we can cancel this out. It's going to be so small. It's going to be basically 0, because we're trying to find instantaneous change in the rate of change. So we're working with very, very small increments of x. We're trying to see what the input approaches as the input approaches 0. So this will be 0. And then we can divide both sides by dx. And we get dy over dx, which is the derivative of this volume function, is equal to 3x squared. And that's exactly what the power rule would give us. Y is equal to x cubed. Throw the exponent in the front and subtract 1 from the exponent. So that's our check to show that we did it right. And yeah, there we have it. That was a visualization of the power rule. See if we have any questions in the comments. Yeah, that cube got really messy. All right, we got like 3 people watching. If you guys have any questions on this, if not, I'm gonna do a quick erase. No questions? All right. And I'm gonna be calling it a day. Thanks for watching, guys. Don't forget to subscribe and hit the notification bell if you enjoyed this video to see more content like this. I'll try to do more of these live stream type videos. I hope this brought value to you. Nice visualization of the power rule. If you guys don't know, this YouTube channel 3 Blue 1 Brown, he does a lot of like geometrical approaches to calculus that I think you guys would like. So I'll try to throw his channel in the description, the link to his channel in the description afterward. And yeah. All right. I'm gonna call it a day.